Okay, so I'm going to work the assignment 9 key here. So just if you have any questions about this, hopefully this will help. I'm going to post a solution to Moodle. I haven't done that yet, but by the time this makes it onto YouTube, that solution should be up. Okay, so here's the problem, or at least the one that I had you turn in. Turn this one via Moodle. Okay, determine the amount of energy you must supply a 50% efficient pump. So if we get into our givens, you know, we know that, so this tells us that eta is 0.50, and to lift 60 liters per second. So 60 liters per second, if you convert that, that's 0.060 cubic meters per second. To the exit at point 2. Okay, so that's open to the atmosphere right here. And the pressure at points L, M, and a point at the bottom of the 6-meter arrow. So I'm going to call this point N. Okay, and we'll do them in order. You may assume no head loss, so we'll solve this problem or something like this with head loss some other time. Okay, so this is a, so, I guess I'll, write down the tools because that's always good to kind of remind ourselves what we have to work with here. I'll probably forget them, but I think, this will be good. Okay, so we've got continuity, okay, geometry. I know momentum is down here. Energy. And of course, hydrostatics. Okay. Okay, and that's usually a manometer. Okay, so in this case, what we're looking for, so the first problem is required. So the first problem is we want to know the amount of energy. So W dot to the pump. Okay, and then the second part, we want to know pressures at L, M, and N. M and N. Okay. So in order to kind of get at this first one, if we're thinking in terms of tools, okay, this first one, well, that has to be energy because, it's asking for power. Okay, so the only way to get at power is with energy because we're going to have to get the head of the pump. Okay, and then these other three, these could be, they could either be energy or hydrostatics. Okay, that's kind of how you always get at, that's how we always get at pressures. The problem is we can't really use hydrostatics here because there's no manometer. So all of these points, L, M, and N, are all in, like, the fluid is moving at those locations. So we cannot use hydrostatics here. So we're going to have to use energy equation for those. So for all of these, basically, energy is going to be our master equation. So let's go ahead and I'm going to try to kind of get at this first one, which is going to be P1 over gamma plus Z1 plus alpha V1 squared on 2G plus HP equals P2 on gamma plus Z2 plus alpha V2 squared on 2G plus HT plus HL. Okay, so I'm gonna use red here, and I'm just gonna kind of knock out the things that we're not even gonna worry about. Okay, so right now I'm gonna cross out the turbine because there's no turbine in this problem. I'm going to cross out the head loss because it says up here you may assume no head loss. Okay, other than that, I think we're going to have to give some serious consideration to most of these things. Okay, so P1 is right here, okay, on the surface. P2 is right here. In both of these cases, it's atmospheric pressure, so this term is going to go away. The pressure term is going to go away, okay, assuming we're working in gauge. A lot of you guys worked in absolute. I don't know why you chose to do it that way, but that's up to you. Using gauge is going to make this easier because that's a 0. Okay, so in both of those cases, it's open to the atmosphere. Okay, now Z1 is right. We're going to call this our datum because that's going to make our lives easier. So Z1 is going to be 0. Z2 is going to be, looks like it's going to be about 10 meters. Okay, because we've got 4 meters here and 6 meters here. Okay, and then V1, so if we look at this term, this is going to go to 0 because of what I like to call the Tahoe assumption, okay, or the tank or whatever. It's really large, so we're going to assume that the surface is not moving. And then V2, okay, V2 we don't know. Okay, so we're going to have to get this from continuity. Okay, so I'm going to do a little aside on that. Okay, and then the HP, of course, is what we're looking for. All right, so let's kind of move over here and we'll do continuity real quick. Okay, so we'll say Q equals V, well, I'm going to call it V pipe, A pipe. Okay, and the reason I'm doing that is because it's going to apply all along that entire pipe because it has a constant diameter. Okay, so the Q is 0.060 cms. Okay, and the V pipe, the area of the pipe is pi times 0.1 meters squared divided by 4. And so the V pipe equals, again, we're going to keep 5, 7.6394 meters per second. Okay, so we can use that in our equations. And then I want to check, while I'm over here, I'm going to go ahead and check the alpha. So I'm going to go ahead and do a Reynolds number equals V times D divided by nu. Okay, so the Reynolds number is, the V is 7.6394 meters per second. The diameter is 0.1 meters. And the viscosity of water is more or less 10 to the negative 6 meters per second squared. Okay, at a reasonable temperature, that's about right. Okay, so I never recommend more than 2 sig figs on this. Okay, but as you can see, this number is much, much larger than like 2,000. So this means it's turbulent. So if it's turbulent, alpha is, well, it's 1.05, but we make it equal to 1, okay, by convention. Okay, so we're good now. So we know the velocity of the pipe. Okay, this is the average velocity, mind you. Okay, and we know the Reynolds number. So everywhere where, you know, we're dealing with a velocity in the pipe, this is our value. Okay, so let's get back over here, and we're going to use those numbers. Okay, so I got HP equals 10 meters plus alpha, which is 1.0, times this V squared, 7.6394 meters per second squared over 2 times 9.81 meters per second squared. Okay, so if we add all those up, HP equals, now I'm gonna split this out. As you guys have probably noticed, I like to do this, 2.9745 meters. Okay, now always be careful with these to remember that square. That's the most common error. And so what I want to remember here, well, I'll solve it real quick. So obviously it's 12.975 meters. Okay, so that's the head of the pump. And then we can go ahead, and from there I can get the power of the pump, or the power the pump supplies to the fluid, which is going to be gamma HP Q. Okay, so gamma is 9810 newtons per meter cubed. HP is 12.975 meters, and Q is 0.606 meters, 0.60, CMS. CMS, okay. So W dot pump equals, if you multiply all of those, you get 7.637.1 newtons times meters per second. Okay, so W dot of the pump is 7.64 kilowatts. Okay, so we would report this number. Okay, so if we want to know W dot to the pump, okay, so that's how much energy I have to give the pump in order for it to give this amount of energy to the fluid, right? I'm going to have to divide that number, 7,001 watts, divided by that efficiency. Okay, and so I'm going to get 15,274 watts. So W dot to pump equals 15.3 kilowatts. Okay. So the points of interest here that we want to consider is this means to supply. So I have to, like if I'm plugging this pump in, my generator or my house or whatever is going to have to generate this much energy in order for the pump to supply this much energy to the fluid. That much energy to the fluid is going to add this much head to the flow, which is going to have the effect of raising the water by 10 meters and giving it this much velocity head. Okay? So that's the physical way to think about this. Okay, so we need to supply this in order to make all this happen. Okay, if we supply less than 15.3 kilowatts, well, if we did 15, well, then we would only get 17.5 would go to the water. 7.5 kilowatts would go to the water, which means we'd have slightly less head. The pump would give slightly less head, which means we could still raise it that velocity, that elevation, but we wouldn't be able to get it to go there quite as fast. Okay, and so that's kind of how this all works. All right, so that said, we're going to do the B part, and in the B part, we are going to, let's see, where should we do B? I guess we can kind of squeeze it in over here, maybe. I guess we'll see. Okay, so the nice thing is I'm going to kind of leave this A part where we can see it, because that's going to be key. Okay, and I do want to be able to see my diagram. Okay, so in B, we want the pressure at L. So P1 over gamma plus Z1 plus alpha V1 squared on 2G plus HP equals P2 on gamma plus Z2 plus alpha V. Oh, this is not a 2. This is an L. These are L's. VL squared on 2G plus HT plus HL. Okay, once again, we're in a nice situation. There's no turbine, there's no head loss. Okay. The other thing that's really nice is if I look right here, okay, because I'm using the exact same point, all of this stuff remains 0. Okay, just like in the last time, all of this became 0. I can do the same thing here. So the right hand of this equation becomes 0 plus. Now between 1 and L, I don't have a pump. So the pump goes away because we don't have one. Okay. And we're left with PL, which is what we're looking for, over gamma, plus ZL. Well, L is up 4 meters, plus. Okay. Now this VL is the same as, is the exact same as this right here, which we're going to use again and again in this problem. Okay, so we've already calculated this value. That's how much velocity head we need. So we'll go ahead and put it in right here, 2.9745 meters. Okay, so what's interesting here is, so we started out with 0 pressure, okay, because we were atmospheric. We don't have a pump between those 2 points. So, and in the meantime, we gained elevation and we gained velocity head. Where did that have to come from? Well, in order to gain those two, we had to lose pressure. And if we started at pressure of 0, pressure is going to end up being negative. Okay, and in feet, the pressure head is negative 6.9745, but in normal kind of in pressure units, it's negative 68.420 newtons per meter squared. Okay, which equals negative 68.4 kPa. Okay. As an aside, we could, when we get a nice negative number like that, we could say, well, what does that mean for cavitation? So PL in this case, if I change that to absolute, okay, basically I'm going to add 101.3 kPa because that's the atmospheric pressure. Then this is 32.9 kPa, okay, absolute. Okay, so if I want to compare that, I'm going to compare that to the vapor pressure, P vape, at 20 C is 2.34 kPa. Okay, absolute. Okay, so notice that this is much higher than that, so there will be no cavitation. Okay, and that's an important thing to consider. Okay, but of course this question didn't ask that. It really just wanted to know, what's this value right here. Okay, so we have that value. All right, so let's do part B, or the next one, which I think we'll go with point M. So M is all the way up here. Okay, so we're basically going to repeat the process. Don't do that. PM on gamma plus Z1. No, that's no good. Okay, P1 Z plus alpha V1 squared on 2G plus HP equals PM on gamma plus ZM plus alpha VM squared on 2G. These get to bar. Plus HT, which we don't have, and head loss, which we do not have. So again, between 1 and M, there's no turbine, there's no head loss. Okay, this is because it's given, and this is because there just isn't one. Okay, so again, this whole thing right here is going to go away because I use the same point. So this is going to be 0. The head of the pump in this case matters because between 1 and M, the pump exists, and the pump is supplying 12.974 meters. Okay, equals PM over gamma plus ZM. M is up. It's like M is up 8 meters. Plus, we got the same velocity head, so we're just going to use that number again, 2.9745 meters. Okay. So if we note this, the math here is that those two add up to 10.97, blah blah blah, and this is 12 points. So the pressure head here is about 2. It's 2 meters. Okay, so PM on gamma is 2 meters. Okay, which makes perfect sense really because we are 2 meters from the exit. Okay, so if we look up here, we're 2 meters from the exit. So from here up to there, it's 2 meters. Okay, and you say, well, but it's not hydrostatic because it's moving, right? And basically, it's got the same velocity head at the exit as it does right here. So that hydrostatics is still playing a role. It's just that because the velocities are constant, it's still the hydrostatic still holds. Okay, so if we solve for this, PM equals 2 times 9810, which is 19,620 newtons per meter squared. Okay, and if we want to report it, we'll go 19.6 kPa. Okay, beautiful. Okay, so now we'll get our last point. And you can see, these are kind of just taking a familiar pattern. And hopefully you guys saw the reason I assigned this, because obviously, these can get a little repetitive, but it's like, why is Wagner making us do this 3 times? This is a waste of my life. I like to believe no, but there was something to be seen. Okay, Vn squared on 2G plus HP plus HL. Okay, again, between 1 and N, there's no pump, there's no head loss. Okay, again, this thing, because I keep using the same point with the same datum, is 0. The pump has the same number, 12.974 meters. Okay, Pn on gamma plus Z of N is 4 meters. Okay, because we can see right here it's 4 meters up. Okay, same velocity head, which is 2.9745 meters. Okay, so again, this side's going to be 6 point. So if we subtract these, the Pn on gamma equals 6 meters. Okay, again, we're 6 meters from the top and there's no pump or anything like that, and the velocity head's the same. So that makes perfect sense. So Pn on gamma equals gamma times 6, which is 58,860 newtons per meter squared. So Pn on gamma equals 58.9 kilopascals. Okay, so that's it. That's the whole problem. And the only thing that I would mention about all this that I think is, before I completely sign off, is that if I look at this, well, that's not really what I wanted to do. If I look up here at all of this business, okay, all this stuff going on, and I think about the pressure in the pipe. Okay, so I want to zoom in here and I want to think about our answers. Okay, the pressure here is 0. Okay, as we move up here, the pressure is decreasing, okay, until its lowest point, which is at point L. The pressure right here is negative 68.4 kPa. Okay, and it lost, well, really it's the same from here all the way across because there's no head loss. Okay, all in here it's the same because there's no head loss. But it was losing pressure because some of that energy right here, where it essentially had, nominally it had 0 energy, right? Because the pressure was 0, the Z is 0, and the velocity was 0. So nominally down here it has no energy, okay? And as it goes up here, the velocity went to something. It went, the velocity head went to 2.9497 or 98 or whatever, right, meters. And the Z went to 4 meters. So both of these went up, so this had to go down, okay? And actually, let's put this in terms of P on gamma. What was P on gamma? 6.9. Yeah, so we could do this in terms of P on gamma, and we could say this was negative 6.98, right? So these two went up, so this one had to go down in equal and opposite measure, okay? Then we hit this pump, and the pump gives it a whole bunch of energy, right? So that's why we're looking at this point right here. And at this point, the Z is the same, 4 meters. The velocity head is the same, 2.98, okay? And the velocity head has to be the same because of continuity. So we gained pressure. And so if we look at that particular problem, that's at point N, okay? We ended up with P on gamma of 6 meters, okay? So P on gamma equals 6 meters. Okay, well now we're all positive, right? And we have to be positive because otherwise we're not going to be able to climb this little mountain right here. Okay, so total now we've got 12.98 meters of head. Okay, and it's all because the pump added head, right? Because we started at 0 and now the pump has added 12.98 meters of head. Okay, which is divvied up by 4 meters of elevation, almost 3 meters of velocity, and 6 meters of pressure. Okay, as we climb, okay, that pressure is going to be converted to elevation, okay, until we get here. So when we get there, Z is now, I guess Z is going to be 8 meters. V squared on 2G is still going to be 2.98 meters. And P on gamma is now 2 meters, okay, because we've lost elevation, we've gained elevation at the expense of pressure, okay? And so that's kind of how we walk through this. Anyway, that's it. Kind of a long video, but I hope this helps. I hope y'all are doing well, and I'll get those tests graded. I'm going to be working on it this afternoon. So have a good one. Cheers. I have to